All right, guys. So here we go. This is the projectile motion, and after this, we will get into some examples and then the simulation that you guys can play with.
Hey, it's Professor Dave. Let's learn about projectile motion.
He knows a lot about the science stuff. Professor Dave explains.
We learned how to use kinematic equations to describe the motion of an object moving horizontally, like a car, as well as objects moving vertically, like objects falling straight down to the ground. But what about objects that move in both of these directions? This type of motion, if it involves an object that is thrown or launched into the air, can be referred to as projectile motion. Imagine a cannonball being fired at some angle from the horizontal. It will travel some distance up into the air before eventually falling back down and hitting the ground some distance away from the cannon. And we can use a parabola to represent the path of this object. The important thing to understand about these kinds of examples is that the horizontal motion and vertical motion of the cannonball are completely independent of one another. This means we can use separate equations to discuss the motion in each direction. One equation that exclusively corresponds to the x-coordinates of the object, and another that exclusively corresponds to the y-coordinates of the object. To drive this idea home, consider two marbles, one dropped from a particular height and another that rolls off of a surface at that same height with some horizontal velocity. If these begin falling at the same time, they will strike the ground at the same instant because their vertical motion is independent of any horizontal motion. The one with horizontal velocity will cover some distance in the x direction, but it will fall downwards at the same rate as the one that falls straight down, and so they will have identical air times. How can we apply this to other real-world examples? Well, we have been throwing lots of rocks off of cliffs lately, so let's throw one more. This time, let's throw a rock at an upwards angle of 30 degrees off the horizontal, from the very edge of our favorite 100-meter cliff, and with an initial velocity of 8.5 meters per second. Again, we will ask, how long before the rock hits the ground? And now, additionally, we want to know how far away from the edge of the cliff it will land. First things first, let's make sure we understand how these questions relate to motion in both the x and y direction. The time it spends in the air only relates to y direction behavior, because it will stop being in the air when it hits the ground. No matter what the horizontal velocity is, from 0 to some huge number, the vertical motion will be independent of that. The distance it travels from the edge of the cliff depends on the horizontal velocity, but also the time it spends in the air, because once it hits the ground, it can't travel any further. And the velocity at any moment can also be split into components. The horizontal velocity will be the same at every moment in this trajectory, as long as we disregard wind resistance. But the vertical velocity will be the greatest at the moment the rock is thrown, and then decrease until it reaches 0 at the zenith, and then become increasingly negative until it hits the ground. This is because there is a constant acceleration in the negative direction due to gravity. We know we can use these equations to answer these questions, but in order to discuss the x and y directions separately, we have to split up this velocity vector into x and y components. This is pretty simple to do. We can simply draw horizontal and vertical vectors starting from the same point as this one and extending precisely as far as this one does in the x or y direction. These can be labeled v sub x and v sub y, and we can think of these as being the legs of the right triangle with the existing vector as the hypotenuse. To find out the magnitude of these vectors, we just do a little trig. We know that the cosine of 30 will be equal to the adjacent leg over the hypotenuse, which means 8.5 cosine 30, or 7.36, will be the initial velocity in the x direction. We also know that the sine of 30 will be equal to the opposite leg over the hypotenuse, so 8.5 sine 30, or 4.25, will be the initial velocity in the y direction. These velocities are independent of one another, meaning that a rock that was thrown straight up with an initial velocity of 4.25 meters per second will land on the ground at precisely the same time as the one thrown at 8.5 meters per second, but at this 30-degree angle. That means that if we want to figure out how long it is in the air, this is no different than a problem with one-dimensional vertical motion, provided that we understand that we are only looking at the y component of this velocity vector. So we can plug the numbers in, -100 for the displacement, 4.25 for initial velocity, and our usual acceleration. Putting it into standard form and plugging into the quadratic equation, we will take the positive result for t and say that the rock will be in the air for 4.97 seconds. This also makes it easy to calculate how far the rock will travel, because we know the horizontal velocity will be 7.36 meters per second, times the 4.97 seconds that it is in the air, which leaves us about 36.6 meters away from the edge of the cliff. So projectile motion is a little more complicated than one-dimensional motion, but if we know how to divide any vector into x and y components, we can easily analyze projectile motion as the combination of two types of one-dimensional motion. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right. Now, we have some examples to look through.
Professor Dave again, let's practice solving kinematics problems.
He knows a lot about the science stuff. Professor Dave explains.
We've looked at the motion of objects in 1 and 2 dimensions, and hopefully the examples we discussed made perfect sense. But many students find that they understand the examples when they are explained, but have trouble figuring out what to do on their own during homework or on a test. The solution to this is to simply practice a lot and use critical thinking skills. We will look at a handful of additional examples now, and as we go through these, the key will always be to ask the following questions. Number 1, what data do I have and what variables are used to represent this data? Number 2, what is it that I am trying to find out? 3, what equation can I use that will allow me to plug in known values for every variable except the one I want to solve for? Notice that each of these 3 equations is missing one of the common variables. This one is missing position, this one is missing final velocity, and this one is missing time. This allows us to do calculations even when there is an unknown parameter. And 4, once you arrive at your answer, does it make sense logically? Or is it way too big or too small to be reasonable? If we are able to think critically in this manner, we will find that many questions in kinematics become relatively trivial to answer. Let's give one a shot. Say you toss a ball directly upward with an initial velocity of 5 meters per second. What will be the maximum height of the ball? Now, as we discussed, let's first decide what we know. We know the acceleration due to gravity. We know the initial velocity. Here's the clever part. We also know the final velocity because at the peak of the trajectory, the velocity will be 0. We are solving for the position associated with the ball when it will be at its highest point. And at that point, the velocity is precisely 0, before it then starts moving in the negative direction. So which equation has all the things we know plus the thing we want to solve for? That would be this equation, where final velocity squared equals initial velocity squared plus 2ax. This is convenient because time is not present, since we have no value for time. Let's plug in the numbers. Solve for x and we should get about 1.28 meters as the maximum height of the ball with respect to the point of release. If we wanted to know its height above the ground, we would just add whatever distance there was between the point of release and the ground. Now let's say we want to know its hang time, or how long it is in the air from the moment you throw it to the moment you catch it at the same point of release. To do this, we can use the following equation and solve for the time elapsed to reach the maximum height, and then simply double it, as falling will take exactly the same amount of time as ascending. We can use this equation because we know both the initial and final velocities and the acceleration. Plugging in those values and solving for t gives us 0.51 seconds. That's how long it takes to reach the maximum height. Simply double that and we get 1.02 seconds as the total hang time. Let's try one more. Say a helicopter is delivering a care package to a remote location. The helicopter is traveling horizontally at 67 meters per second and is at a height of 120 meters when the package is dropped. How long before the package hits the ground, and how far will it travel in the horizontal direction? So the first thing we need to recall is that the vertical and horizontal motion are independent of one another. The package will take the same amount of time to hit the ground, whether there is horizontal motion or not. So we can isolate the y direction to find the time elapsed in the air. We know that the position will be negative 120 meters, since it will travel that far in the negative direction. Initial velocity in the y direction is 0, since the helicopter has no vertical motion, and acceleration is known. Let's plug these into this equation and solve for t, which will be about 4.95 seconds. Now that we know how long the package is in the air, it is a trivial matter to calculate how far it will travel in the horizontal direction. We simply use the definition of displacement. It is traveling with the same velocity as the helicopter the entire time it is in the air, since there is no acceleration operating in the horizontal direction. So 67 meters per second times 4.95 seconds equals about 332 meters. So remember that when solving problems of this nature, always ask yourself what information you have. Also remember that sometimes you may have information that is not explicitly listed in the question. If something is moving from rest, the initial velocity is 0. At the moment that an object changes direction with respect to its vertical motion, the velocity is also 0. Make sure you think critically in this regard. Then ask yourself what the question is looking for and select an equation that will allow you to solve for this unknown value. Let's check comprehension.
All right. Now, here's another link to another simulation that I think is pretty helpful for getting a feel for concepts behind this. There we go. All right. So there's the intro. So vectors. Here you can adjust, change the initial speeds, target, fire. Yeah. Okay, so so play around with this if you want. Obviously don't spend too much time on it. You can change the mass of it. This will actually come in handy later. Gravity, I'd say probably leave gravity. Don't mess with air resistance. We won't be covering anything that deals with air resistance. But yeah, here you can change the height, change the initial speed. Boom. have this to measure. Yeah, so it's a fun little simulation. I enjoy it. Don't mess with drag. That's just the lab, the intro. Intro is probably really it. This guy down. So here we see the angles. Let's kick this up a little bit. Speed. There we go. See this green dot? This green dot is height. Ground height. So you can use this to sort of like check some of your calculations. If you have a problem that is in the book that you're going through, you want to test out, and you sort of want to see how it works a little bit. This is where simulations like this shine. So, all right, that is it for week 1. Make sure you go through the book. Make sure that you go through the practice examples, the knowledge checks, and the terms that are being used. Play with the equations and how they interact with each other. And I will see you, or I mean, you'll have new videos for you at least next week. All right, thank you. Bye. I have to stop this thing. All right. Bye, guys.